All right, it's Matthew Matt coming back at you. My kid watches a lot of YouTube's videos, and they always say to slap the like button. So go ahead and slap that like button. All right, let's talk about some area formulas. We're going to talk about where area formulas come from, or at least one way we can think about where area formulas come from. There's a lot of different ways we can do this, so I'm not attempting to give you a comprehensive overview of every way of thinking about it. I just want to give you a big picture look at how we can derive formulas for more complicated shapes by starting with more basic shapes. All right, let's talk about rectangles first. They're pretty straightforward. I've got a rectangle, and I'm going to go ahead and measure the length here. And as I'm measuring the length, I'm figuring out that it's 5 units long, but I'm also figuring out that I can fit 5 squares in a row of that rectangle. And then as I go ahead and measure the other dimension, I see that it's 3 units wide, but it's also telling me how many rows I can fit. So now I can think of this as 3 rows with 5 squares in each row, or as an array of 3 by 5, which are concepts kids should have been working prior to doing area. So that gives us the formula we're familiar with, or that many of you learned in school, which is that area is length times width. All right, let's talk about parallelograms, and I'm going to call this strategy the cut and move strategy. I'm sure it's one many of you have seen before. I've got a parallelogram, and I have this side piece that I don't really know how to deal with, so I'm going to cut it off and move it over, and now I have a shape I'm familiar with, which is a rectangle. So essentially what I've done is I've taken this parallelogram, which has a base and a height, and turned it into this rectangle, which has the same base, which we call a length sometimes with rectangles, and the same height, which we sometimes call the width with rectangles. So we just use our old formula for rectangles, length times width, or we're going to rename them as base times height for a parallelogram. So basically what I've done is I've taken the parallelogram, cut it up, and rearranged it so it looks like a rectangle that I know how to deal with. I want to talk about a different strategy with parallelograms, which I'm going to call Enclose. So the old strategy for parallelogram works great, but it doesn't work so well for a parallelogram that looks like this. If I think of this as my base, and this is my height, then if I try to cut this piece off and move it over, I'm left with something that's not super helpful. Now I could put the parallelogram on its side so that it's sitting flat on the long side, and then the old strategy would work fine. But I also want to be able to think about how this bottom, this short little side, can be a base. So I want to talk about a different way of thinking about this parallelogram. If I want, I can think of it as sitting inside this rectangle. And then essentially I've got a rectangle, and I need to subtract off these 2 triangles I don't like. The orange triangle and the blue triangle are not part of my parallelogram, so I want to subtract them. One way to do that is just to slide that orange triangle over and turn it into a rectangle. So essentially what I've done is I've turned the parallelogram on the left into the rectangle on the right just by sliding that triangle over. And I haven't lost any area because all I did was move pieces around without overlapping anything. And my parallelogram and rectangle have the same base, and they have the same height. And I know how to do base times height for a rectangle, so it must work for my parallelogram also. So I've got area equals base times height. I'm going to talk through triangles, and I'm going to show 3 different kinds of triangles and how we can think about where the area formula comes from for them. So right triangles are pretty straightforward. We basically already did this on the previous video. I can think of my right triangle as half of a rectangle, and that has a base and a height, and the triangle is half of that, so I've got area is 1/2 base times height. All right, I'm going to call these double right triangles, which is certainly not a mathematical term, but I think it applies. So I've got a triangle that looks like this, and part of how I can think about this triangle has a base, this triangle has a height, and part of how I can think about my triangle is as split up into a red triangle on the left and a blue triangle on the right, and these are both right triangles, which are a little more easy for me to work with. I'm going to enclose this whole thing in a rectangle again, and now I can see that the red triangle is half of this side, and the blue triangle is half of the right side. And so when I put those ideas together, I see that the whole triangle has got to be half of the whole rectangle. I just want to say that again. Because the red side is half, the red triangle is half of the left side, and the blue triangle is half of the right side, that means the whole triangle must be half of the whole rectangle. So that gives us, again, our formula that the area is 1/2 base times height, because I already know how to find the area of that rectangle, which is base times height. All right, finally I'm going to talk about a Whopper jawed triangle. Those two strategies work well for other triangles, but they're a little trickier when it comes to a triangle that looks like this. Again, I could turn it and put the long side on the bottom, but if it's not, if I want to treat this bottom as the base that I have here, I need some other strategies. So I've got my base and my height. And if I wanted to, I could put a rectangle around it, and I could subtract this red triangle, and I could subtract this blue triangle, and I could do some algebra, and I'd end up with the formula I wanted. But I want to show a little different way of thinking about it. So what I'm going to do is take this triangle, I'm going to copy it, and I'm going to spin it around, and I'm going to end up with a shape that I know what to do with, which is a parallelogram. I already know a parallelogram is area is base times height, and my triangle is half of that, so I again end up with the formula I wanted, or that I'm familiar with. All right, to summarize, I want to talk about the idea that we should build the concept for the area of a rectangle should build on earlier meanings of multiplication for kids. The idea of groups of, that I have 3 rows, or groups with 5 squares in each group or row, and this notion of an array, of a 3x5 array, both of which are things they should have been working with before developing area formulas. And then I can find out the formulas for more complicated shapes based on that, essentially by cutting shapes up and moving them around until they look like something I like. Now there's a lot of ways we can do this. I only showed you a couple. One approach that can be used for a lot of shapes and that connects more to calculus concepts is to cut the shape up into lots of teeny little rectangles and then move those pieces around until it looks like something we want. I want to highlight 2 of the strategies we saw, which is taking a parallelogram and surrounding it with a rectangle, and thinking of triangles as half of a parallelogram. We often see triangles as half of a rectangle, but I wanted to highlight how they can also be thought of as half of a parallelogram because it's a more general strategy. Coming up next, I'm going to ask you to think about where the formula for the area of a trapezoid comes from. This is something for you to play with and explore. You're not going to hand it in. It's not going to be graded. I just want you to think about it and think about where this formula might have come from.